Today I'm finally ready to talk about the proof that differentiating arbitrary vector p expressed in frame B, the vector itself is expressed in frame B, but we take time derivative in frame with respect to frame I. It is equals to, you take the same vector, do the time derivative in frame B itself, plus a relative rotation vector, the rotating speed vector, expressed in frame B with respect to frame I. So in terms of rotation, right, always we need to talk about A with respect to B, or you have to have some reference. In this case, the reference is the inertia frame I, and the rotating frame is the body frame B, while the rotating speed itself is of the frame is omega, and since this is a vector, it can be kind of expressed in frame B, just like this vector is expressed in frame B, and then this speed cross product with the the vector expressed in B, essentially the vector itself. So this equation is kind of difficult to understand initially, but we will prove today. And in last video, I actually already proved some theory that will be helpful for us to understand the proof for this. Essentially, when we comes to this part, I need to use the conclusion that we derived last time. So if you haven't watched the video last time, please watch that. And before we going into this kind of proof, I just want to briefly overview the frame, and when the frame is rotating across certain axis, the axis of rotation. Just review a few concepts. This IB height, JB height. We use this superscript to describe. Sorry, I should use a superscript here to describe that this is in body frame. We use this height notation to express it as a vector which has a direction, and these three are actually called unity vector, which it has the length of 1. That's why it's called unity vector. And this frame itself is we usually use B as body frame, which is a rotating frame, and we had a video cover body frame and the inertia frame as well, and we use I as our inertia frame, which is essentially doesn't move. If you're not clear about concept, please review the video talking about inertia frame and body frame. This is essentially a frame that is rotating against axis of rotation, where the rotating vector omega b dash I itself, we express it as a kind of a normal vector here, right? The only thing that makes it special versus like just a force vector, for example, is that this kind of rotating vector, it has a direction in aligning with axis of rotation, but the actual that's the direction of the vector. However, the direction of the rotation needs to be judged by right-hand rule, where you point your thumb to the rotation direction of the vector, and then your curve direction will be the actual angular rotation, like that. And the magnitude is of course this one, and similarly we could use like a unity vector notation like this. So usually we use once we have this kind of height, we assume it is a unity vector. While if we express things like underline here, it means the total kind of vector has a magnitude part, and it has a direction as well. So this is the way that we express the rotation here. And because this is a vector, right? This is a vector in a 3D domain. Similar to like how you express a standard vector, you could actually use the projection to project this vector, for example, on your axis, this 3 axis, so that it can be decomposed into three portions, just like how you handle the standard vector. Essentially, what I'm trying to say is, if we decompose this vector, right, for example on the GB axis, then essentially it will have a magnitude like that, and then since the GB direction is in this way, when we project that like that, what does it mean physically? It means that you have a right-hand rule, and you point a thumb into this unity vector direction, and then your positive, like a definition of omega, project here will be essentially rotating like that. And because this projection is obviously a negative value, so that means just means when you project this vector here, it actually, instead of rotating like that, it rotating in the other direction. So that's just give you some physical meaning of that. But in terms of vector itself, it might be, for example, -3, 4, 5. I'm just making it up. It just means this is like some value, rotating. It's projected onto the x-axis, which is I-axis. So the right-hand rule. This means you can actually decompose the rotation vector into 3 portions, just like what you do with the normal vector, right? Similarly, k, in the k case, you have the right-hand rule, point, you align your thumb with the k direction, and then you have a rotation like that. And when these numbers are positive, you truly rotates like that. When it's negative, you rotate backwards. And magnitude, of course, is the angular speed. So that's all the beauty of the framework that people set up to express the rotation in a 3D frame, and it can be expressed in this kind of rotating frame, body frame in this specific case. So with that background, let's start proving this equation. And this equation will be kind of useful when we talk about the differentiation of, for example, force vector. Second Newton's law. For example, like differentiation of force vector in a rotating frame. We will do that in the next video, but let's prove this theory first. Um, Essentially, if we want to differentiate this vector, let's first let p be an arbitrary vector, and then when we express that in inertia frame, you express that vector in inertia frame. It's a projection px, py, pz in the inertia frame, and as well as its unity vector. That's just a very standard thing. And then if we take the derivative directly in the inertia frame like this, actually right now we are not talking about taking derivative in the inertia frame. We're just in general taking a time derivative of this vector expressed in inertia frame. We're not talking about with respect to which frame yet. It will become a little more clear when we derive this part, but essentially this is equals to there's a, when you take derivative, there's a theory that if you have, in this case, if you have a u times v, if you take time derivative of that, it is equals to u dv dt plus like v du dt. We take this property and apply it here, which essentially derivative of that against time is equals to the px time derivative plus the this part times the derivative of pxi. So similarly, we have the y-axis and z-axis. And interestingly enough, because the rotating frame like inertia frame, it doesn't move, right? So that's why this unity vector in inertia frame, it is also called north-east down frame. And this frame is like fixed; it doesn't rotate in any way. That's why this unity vector doesn't change as well. It doesn't have any linear velocity, so this goes to 0, right? So similarly, this go to 0, this go to 0, and does this actually seem familiar? It is essentially taking derivative in the x-axis, in the y-axis, as well as in the z-axis, right? Nothing special. This is what we are usually familiar with. It's taking derivative, just taking derivative with like this direction vector fixed and nothing else. This is more formally defined as taking a derivative of a vector in the inertia frame. Time derivative is equals to just taking the projection of that vector. Essentially, your x component takes time derivative, y component takes time derivative, z component takes time derivative. This is easy to understand, simple. While this one becomes a little bit tricky, if we have this vector expressed in body frame, which is a rotating frame, it's still the projection but onto the body frame, so this unity vector are a little bit different. It's the unity vector of body frame, and when we take that time derivative, the same principle applies, the same rule applies, and we can wrote like that. But what is interesting is these terms now is not there anymore, because this not necessarily 0. It depends on when you take this derivative, you are taking it with respect to which frame, but essentially it's not as simple as inertia frame. When we do time derivative of the body frame like that. We actually in last video we proved that time derivative of this unity vector is actually equals to the rotating speed vector of the angular velocity of the frame B in frame I, cross product with the vector itself, right? The unity vector itself. So we proved this. That's why you can actually substitute this here. And again, it's not zero. If it's zero, it will be as simple as inertia frame. But this is like a more general case, right? We haven't talked about. We are just taking a time derivative. We haven't talked about with respect to which frame. And be careful here. Now we are talking about time derivative with respect to inertia frame, and the reason that we can do this substitution is because we are doing this with respect to inertia frame. And even last video when we try to prove this, right, we are proving this theory against inertia frame. So the frame doesn't rotate. It's a B with respect to I is the rotating frame in an inertia frame. So that's why I was saying this is like more general. But when you try to map this using angular speed vector like that, the body with respect to inertia, really we're taking time derivative in the inertia frame. So you are taking a vector of a body frame rotating vector and take a time derivative of that with respect to the inertia frame. That is actually equals to you are taking the same vector and taking it against your body frame, and this specifically is trying to say that there's no rotating involved. You just map that vector in your body frame like a vector, whatever value, those three values. They might be a function of time, and then you just take the derivative with respect to time. There's no rotating frame involved. So you have a vector expressed in body frame. You take the time derivative inside the body frame. So reference point is body frame. That's why body frame doesn't rotate against body frame. So that's why this part doesn't have the rotation involved. Where when we talk about this part, it is the effect of rotating, because the body frame is rotating against the inertia frame, and we proved that this derivative of the unit direction B against the inertia frame, it is equals to this velocity vector cross product with the unity vector. And then you have the magnitude here. So similarly with that, we can collect all the atoms because this is a scalar, so you can move it inside, and then by doing so you can see these three are just lumped together to be this part, which is the vector P in body frame itself. That's where you have this one. And then again, we are taking we are looking at this vector, and we are taking a time derivative in inertia frame, and that is equals to the same vector you take a time derivative inside the body frame, and then that plus the velocity vector. Again, we're talking about the vector, right? We at the beginning of this video we are talking about, the rotation can be actually expressed in a vector format, and this vector is the frame B rotate against frame I. That because that's a vector we actually project it onto the frame B. That's what this notation says, and we use that vector and then cross product with the arbitrary vector P, or the vector of interest. That's how we proved this equation, where you are taking a time derivative of a vector expressed in frame B, relative to frame I. You are an observer, for example. You stand in frame I in inertia frame, and you are looking at a vector that might be changing in magnitude, might be changing in direction, whatever. But you project that onto the body frame, and then you take the time derivative inside the inertia frame. It is equals to taking the same vector. You take time derivative inside the body frame, so there's no rotation here, and this is only time derivative, no rotation, and the rotating effect is essentially separated out here. Is your frame B rotating against frame I, where the speed is magnitude is omega, and then this is a vector. We can express that in frame B, just like a normal vector P, and then use that cross product with the vector itself. So hopefully this is clear to you. If not, I would recommend you watch inertia and body frame, as well as watch how I proved the time derivative of unity vector is equals to the rotation of the frame cross product with the vector itself. And in next video we're gonna take this and apply it to a new second Newton's law, which there is a force factor, right, is equals to your mass times a, which is the acceleration, and we will say that because of this frame difference, the Newton's law could looks a little bit unfamiliar to you, different to you when you do that, express that Newton's law in a different frame, especially in a rotating frame. Thanks.